Best time to buy and sell stock. Have you ever wondered how top engineers spot patterns that lead to big wins? Best time to buy and sell stock is not just a must-know pattern mastery 100 question. It appears in almost every FONG interview loop and stumps over 40% of applicants. Mastering this problem gives you an edge in any technical interview because it teaches you to recognize profit opportunities, optimize for efficiency, and think like a Wall Street pro. Ready to discover the secret? Let's dive in. Let's break down the problem. We're given an array where each element represents the price of a stock on a given day. Our job? Find the maximum profit we can achieve by choosing a single day to buy and a different day in the future to sell. If there's no way to make profit, return 0. No short selling, and you can't sell before you buy. Let's assess our options. A naive brute force solution would check every possible pair of buy and sell days, but that takes n² time, not scalable for big inputs. Instead, can we track the lowest price seen so far and always check the profit if we sold today? This only needs a single pass and 1 extra space. Super efficient. Remember, always buy before you sell, and update your max profit as you go. Here's the structure of our plan. Start with variables for the minimum price so far, set to infinity, and maximum profit, set to 0. Loop through each price in the array. If the current price is less than the minimum, update the minimum. Otherwise, calculate the profit if we sold today, and update max profit if it's higher. Let's try to implement it using solution 1. We're defining a function called max profit that takes an array prices, where each value is the stock price on that day. We create a variable min price and set it to infinity, so any real price will be smaller and can replace it. We also create max profit and set it to 0, because the minimum possible profit is 0 if we never find a good trade. Now we loop through the prices array. Inside the loop, we store the current day's price in a variable called price. If the current price is smaller than min price, we update min price to this new lower price, because that's a better day to buy. Otherwise, we check if selling today would beat our best profit so far. We calculate today's profit as price, min price. If that profit is bigger than max profit, we update max profit to this new larger value. Once we finish the loop, we return max profit as the best possible profit. Time complexity is O(n) because we scan the array once. Space complexity is O(1) because we only use a few variables. Let's verify solution 1 for best time to buy and sell stock. Input is prices equals 7, 1, 5, 3, 6, 4. We start with min price as infinity and max profit as 0. Day 0, price is 7. 7 is less than infinity, so min price becomes 7. Day 1, price is 1. 1 is less than 7, so min price becomes 1. Day 2, price is 5. Now profit would be 5 minus 1, which is 4. 4 is greater than 0, so max profit becomes 4. Day 3, price is 3. Profit would be 3 minus 1, which is 2. That's not greater than 4, so max profit stays 4. Day 4, price is 6. Profit would be 6 minus 1, which is 5. 5 is greater than 4, so max profit becomes 5. Day 5, price is 4. Profit would be 4 minus 1, which is 3. That's not greater than 5, so max profit stays 5. We finish the loop and return 5. The output is 5, and the expected is 5. They match, so solution 1 is correct for this test case. Let's try to implement it using solution 2. We're defining a function called max profit that takes an array prices, where each value is the stock price on that day. We create max cur and set it to 0. This represents the best profit we can have if we end the trade on the current day. We create max so far and set it to 0. This stores the best profit we've seen anywhere so far. Now we loop starting from index 1, because we'll compare each day to the previous day. Inside the loop, we calculate diff as today's price minus yesterday's price. This tells us whether the price went up or down. Next, we update max cur using math.max0, max cur plus diff. That means we either extend our current profit streak by adding diff, or if it becomes negative, we reset back to 0, because we're better off starting fresh. Then we update max so far using math.maxmax so far, max cur, to keep track of the best profit we've ever seen. After the loop ends, we return max so far. Time complexity is O(n) because we scan the array once. Space complexity is O(1) because we only use a few variables. Let's verify solution 2 for best time to buy and sell stock. Input is prices equals 7, 6, 4, 3, 1. We start with max cur equals 0 and max so far equals 0. At I equals 1, diff is 6 minus 7, which is negative 1. Max cur becomes max of 0 and 0 plus negative 1, so max cur becomes 0. Max so far stays 0. At I equals 2, diff is 4 minus 6, which is negative 2. Max cur becomes max of 0 and 0 plus negative 2, so max cur is 0. Max so far stays 0. At I equals 3, diff is 3 minus 4, which is negative 1. Max cur stays 0, and max so far stays 0. At I equals 4, diff is 1 minus 3, which is negative 2. Max cur stays 0, and max so far stays 0. We finish the loop and return 0. The output is 0, and the expected is 0. They match, so solution 2 is correct for this test case. Let's have a quick recap for best time to buy and sell stock. This problem is a clean test of whether you can make the best decision over time, using only one buy and one sell, and still stay efficient. You're given daily stock prices, and you want the maximum profit from a single transaction. Buy on one day, then sell on a later day. The buy has to happen before the sell, and if the prices never give you a profitable opportunity, the correct result is simply 0. A direct approach of checking every possible buy and sell pair makes sense at first, but it becomes inefficient as the input grows. The stronger idea is to track key information as you go. Keep the lowest price you've seen so far, and compute what profit you'd get if you sold today. That turns the problem into a single pass with constant extra space. The plan is built around a simple loop with two trackers, one for the minimum price so far and one for the best profit so far. Each day, you decide whether the current price becomes your new best buying point, or whether selling today would improve your maximum profit. This step-by-step process naturally discovers the best trade without needing nested checks. We implemented that logic and it ran successfully on LeetCode without errors, processing the prices day by day, updating the minimum when needed, and updating the best profit whenever a better selling opportunity appeared. We validated the approach through LeetCode test cases. For a rising opportunity like 7, 1, 5, 3, 6, 4, the logic correctly identified the best outcome. Buy at 1, sell at 6, for a profit of 5. And for a declining sequence, like 7, 6, 4, 3, 1, it correctly returns 0, confirming the strategy handles both profit and no profit scenarios correctly. The main lesson here is learning to optimize by tracking the right values as they evolve. This is less about stock trading and more about recognizing patterns where a single pass can replace expensive comparisons, making your solution both fast and reliable under interview constraints.